Points of discontinuity. Now, let's begin. In our previous section, we established the fundamental requirements for continuity. We learned that for a function, f of x, to be considered continuous at a specific point, x equals c, it must satisfy three very strict conditions. First, the function must be defined at c. This simply means that when you plug the value c into the function, it must produce a valid, real number. Second, the limit must exist as x approaches. See, this implies that as we approach the point c from both the left and the right sides, the function must be heading toward the same finite value. And third, the limit must be exactly equal to the function's value at that point. In other words, the hole we are approaching must be filled by the actual value of the function. Now, the core of today's lesson is this. If a function fails to meet any one of these three criteria, we say that the function is discontinuous at that point. When this happens, the point x equals c is formally referred to as a point of discontinuity. In the upcoming slides, we will dive deeper into the specific causes of these discontinuities and look at some practical examples to help you identify them. Understanding the causes of discontinuity. Now that we have established the three strict conditions for continuity in the previous slide, let's examine how to actually identify a point of discontinuity. Essentially, we are looking for the specific break or failure in those requirements we just discussed. Generally, discontinuity occurs in one of the following three scenarios. First, the function is undefined at x equals. See, this happens if the function value at c does not exist. For instance, if plugging the value into the equation results in division by 0. In such a case, the function simply cannot be continuous at that point. It is important to note that even if the limit exists as we approach that point, the absence of a defined value creates what we call a hole in the graph. Second, the limit does not exist at x equals c. As a reminder, a limit exists only if the left-hand limit and the right-hand limit are equal. If the limit of the function as x approaches c from the left is not equal to the limit as x approaches c from the right, then the overall limit as x approaches c does not exist. Visually, this typically results in a jump in the graph, where the curve abruptly shifts from one value to another. Finally, there are cases where the limit exists, but it does not equal the function's value. In this scenario, the function is defined at c and the limit exists, but they are not the same value. In other words, the limit as x approaches c does not equal the function of c. This means the graph has a hole at the limit point, and the actual value of the function is plotted as a separate, isolated point located either above or below the curve. Understanding these three causes will help us as we move forward to look at a real-world analogy and some detailed mathematical examples. Real-world analogy, the digital switch. Now that we have discussed the theoretical requirements for continuity and the three primary causes of discontinuity, let us use a real-world analogy to make these concepts more intuitive. Consider a digital light switch. In this scenario, we can represent the state of the light using numbers. The value 0 represents the light being off, and the value 1 represents the light being on. The key observation here is that there is no gradual transition from 0 to 1. The light does not slowly brighten. Instead, the state jumps instantly from one value to the other. If we were to plot this state on a graph over time, the exact moment the switch is flipped would be a point of discontinuity. This is because the value jumps abruptly from 0 to 1 without passing through any of the intermediate values in between. This serves as a practical example of a jump in a graph, which we will analyze using formal mathematical functions in the next slide. Detailed examples. Now that we have discussed the theoretical causes of discontinuity, let us apply those concepts to some detailed examples. This will help us see exactly how the three conditions for continuity we mentioned earlier can be violated. Let's begin with example 1, which demonstrates a discontinuity caused by an undefined point. Consider the function f of x equals x squared minus 4, all divided by x minus 2, and let's examine it specifically at the point where x equals 2. To analyze this, our first step is to check if the function is defined at x equals 2. When we substitute 2 into the function, we get 2 squared minus 4 in the numerator and 2 minus 2 in the denominator. This results in 0 divided by 0. As we know, division by 0 is undefined, which means the function value at x equals 2 does not exist. Because this first condition of continuity is violated, we can conclude that the function is discontinuous at x equals 2. Moving on to example 2, we will look at a discontinuity caused by the non-existence of a limit, which typically creates a jump in the graph. We are dealing with a piecewise function here. F of x equals 2x plus 1 if x is less than 1, and f of x equals x squared plus 5 if x is greater than or equal to 1. First, let's find the function value at x equals 1. Since the second rule applies when x is greater than or equal to 1, we calculate 1 squared plus 5, which gives us 6. Next, we must check the limit. We start with the left-hand limit. As x approaches 1 from the left, we use the first expression, 2 times 1 plus 1, which equals 3. Then we find the right-hand limit. As x approaches 1 from the right, we use the second expression, 1 squared plus 5, which equals 6. When we compare the two, we see that 3 does not equal 6. Since the left-hand and right-hand limits are different, the overall limit as x approaches 1 does not exist. Therefore, the function is discontinuous at x equals 1. Finally, let's look at example 3, where the function is defined and the limit exists, but they are not equal to each other. Consider the function where f of x equals sine of x divided by x for all values except 0, and f of x equals 0 exactly at x equals 0. First, the function value is straightforward. It is explicitly given as 0 when x equals 0. Now, let's find the limit as x approaches 0. From our study of standard trigonometric limits, we know that the limit of sine of x divided by x as x approaches 0 is equal to 1. Now we compare the two. The limit is 1, but the function value is 0. Since 1 does not equal 0, the third condition of continuity is not satisfied. Consequently, the function is discontinuous at x equals 0. These three examples illustrate the three distinct ways a function can fail to be continuous. Keep these in mind as we move to the next slide, where we will discuss some common mistakes students often make when identifying these points of discontinuity. Common mistakes to avoid. Now that we have walked through several examples, let's discuss some common mistakes students often make when identifying points of discontinuity. Avoiding these pitfalls will ensure your analysis is mathematically sound. First, there is a frequent misconception that if a function is undefined at a specific point, then the limit at that point cannot exist. This is incorrect. To illustrate this, let's refer back to example 1 from the previous slide. In that case, the function f of x equals x squared minus 4 divided by x minus 2 was undefined at x equals 2 because it resulted in 0 over 0. However, if you were to calculate the limit as x approaches 2, you would find that the limit actually exists and equals 4. So, remember, a hole in the function does not necessarily mean the limit is missing. Secondly, when dealing with piecewise functions, it is a common error to ignore either the left-hand limit or the right-hand limit. Some students check only one side and assume the limit exists. As we saw in example 2, you must explicitly calculate both the left-hand limit and the right-hand limit. The limit only exists if these two values are identical. If they are different, you are looking at a jump discontinuity. Finally, be careful not to confuse every point of discontinuity with a vertical asymptote. While it is true that a vertical asymptote, such as the one found in the function f of x equals 1 over x, is a point of discontinuity, not all discontinuities behave this way. Some are simply holes, which we call removable discontinuities, and others are jumps. An asymptote is just one specific type of break in the graph. By keeping these distinctions in mind, you will be able to more accurately categorize the behavior of any function. Now, let's move to our final slide to summarize the key takeaways from this lesson. Key takeaways. Alright, let's wrap up everything we have covered in this lesson. To summarize, a function is considered discontinuous at x equals c if it fails any one of the three continuity tests we established at the very beginning. Let's recap the three main reasons why this happens. First, the function value at c, denoted as f of c, is not defined. This is exactly what we saw in our first example, where dividing by 0 made the function undefined. Second, the limit of the function as x approaches c does not exist. As we discussed during the piecewise function example, this occurs specifically when the left-hand limit does not equal the right-hand limit. And third, there are cases where the function is defined and the limit exists, but the limit as x approaches c does not equal the function value at c. This was the scenario in our third example, where the limit and the actual point were at different heights. Finally, it is helpful to remember how these look visually. Depending on which of these three conditions is violated, the discontinuity will manifest on a graph as either a hole, a jump, or a vertical asymptote.